Should we start? Yeah. So the next lecture is on social science, and some of you have heard parts of it. We start with this gentleman. This is a very sad story. He was a very clever young man around 1800. He was a physicist. All of his friends were extremely famous physicists. They were members of the academy. They were discovering all the physical laws. And he said, well, let's do the same thing for society. He called it sociophysics. So he suggested to do the same as the physicists are doing, just for society. And that stopped basically his career. No one was taking him seriously. He was trying it over and over again. To establish this, it did not work. He died as a very sad and poor man. And the only thing that he's really remembered today is that he also created, since no one wanted to hear anything about sociophysics, he also created the term sociology, and it is still around. So he's one of the fathers of sociology. But what he had in mind is physics of society. Yeah? And this was, of course, not possible until now. Maybe still not possible. But until then, it was. Why was it not possible to do physics of society? Because they did not have the concept of statistical mechanics. That was not there. That would be important for society. There was not the notion of. There was the notion of force, yes, that was there, but the notion of multiple forces or something, changing forces, none of this was there. They did not have the concept of nonlinear systems. So it was really extremely crazy of this guy to suggest something like this. So the name, yes, sorry, Auguste Comte, C-O-M-T-E. So, and now 200 years later, we can try to do it again, maybe equally crazy. People in 200 years will say the same thing about us. But we try it again. We want a quantitative, predictive, and testable theory of how societies work and understand them. So what is a society? And sorry, showing this again. This is a society. I'm not going to go into this. We're not going to go into this. Just mentioning it again, we can observe all elements in with big data, we can observe all of these elements. We can observe the networks, how the networks change, the states, and how the states change. Yeah? And if we are able to find out what these functions are, can be stochastic functions, can be deterministic, can be linear, can be nonlinear, can be anything. If we find out what this is, we understand. Okay. As I told you on Sunday, we have the luck to own a massive multiplayer online game where we have about 500,000 registered players. At any point in time, it's outdated, it's about 10,000 players at any point in time. It's an old timer, it is extremely old-fashioned, so if you look at it, you will laugh how old-fashioned it is. It's online since 2004. It's free. You can donate. And it just happened that a student once showed up in my office and he wanted to do a PhD. So I asked him if he liked mathematics. He said, no. You like physics? No. And then when I asked him what he liked, he said computer games. And I had mentally decided to kick him out soon, but to be polite, we were talking a little bit. And then he was telling me that he was the designer of this game. And then I asked him if he had log files, what the players are doing. And when he said yes, we had a deal. And he was assistant professor at MIT afterwards, and is now a professor in Denmark. So that can happen to you if you start programming computer games. So if you're an avatar, you're born into this little bit futuristic universe. It's not futuristic at all. It's just the things look different. You have a car, but it is a spaceship. You live in a house, but it's in a satellite. You live in a city. It's a collection of satellites around the planet. You can go from one city to another city. There's something like a road network, but it's not really a road network. It's called wormholes, where you tunnel through. Basically, the game is completely open-ended. You can do what you want. You cannot be racist, sexist, and you cannot operate more than one character. If you're one of these things, you're deleted and are not allowed to join ever again. That's the rules. And as soon as you start, as soon as you start, typically you start harvesting in fields. It's not fields, it's not rice fields, but it's you're harvesting energy fields and space, steel, and I don't know, and you pack that into your ship and you sell it somewhere else. So you earn a little bit. If you have enough money, you can buy a satellite, you can transform your satellite into a factory, then you can buy things from suppliers and produce your own stuff. There's a whole supply chain that tells you what you can produce. You can produce, for example, drugs or beer. If you consume this has an effect on you. It distorts time. So you can become a seller, you can become a politician or a mayor or a king, or the different cities you have are governed or are not governed. People decide how they want to have it governed. If you don't like how it's done in your neighborhood, you can migrate. You can go to there's 3 countries, same as countries. From time to time, these countries get into war with each other. War is something where 10,000s of people are destroying satellites, so houses and infrastructure of other 10,000s of people, and these go on for months and weeks and months. And so you have 3 components of life. You have an economic life, you're producing, distributing, trading things, you make profit from this, and with this profit, usually you are buying things. Typically, it's status symbols, things that are worth nothing, but make you look better in your local neighborhood. There's a social life. People talk, of course. They talk privately with each other. There's forums. This is like newspapers or television. There is emails. There is blogs, etc. People seem to do everything to accumulate kind of status. If you are participating in a war, or if you're killing a pirate, or if you're saving a city or something, then you get medals of honor or achievement points or agricultural points. And people always try to pick one of these or 2 of these and then try to rise in social status. And there has been exploratory life. So people are trying to figure out, how does this universe work? There's scientists, so some really nerdy players. For example, they put gasoline in their spaceship, then they pass by planets, then they try to measure the gravitational force by seeing how much you consume, and they figure out that the laws of gravity there is different from laws of gravity here. And there's biologists who study the space monsters that are around, and they classify them in a Linnaean scheme. So, and there's even people writing papers about this. And these papers are even peer-reviewed within the game. It's very, very crazy. Almost as crazy as our real life. So the game is 2-dimensional. basically everything is on grids that get finer and finer. You have a spaceship, you have a neighborhood. In your neighborhood, you have certain resources around. There's other ships around. You're close to this planet. So when you're playing, you can zoom in and out of these things. As soon as you put people together, they start organizing. They are building social structures. So you have friendships. So on a very local scale, you have hierarchical, more or less hierarchical groups. You have clubs. You have societies. You have political parties. You have gangster groups, pirate groups. You have cartels, meaning people producing something, they say, let's keep the price up. We have banks. No one ever thought of having a financial system in this game because we did not want to have people take credit, because if they cannot repay it, what would happen is all the instabilities. We did not want to have this. But people invented banks. They built factories. But there was no input, no output. So when we looked what was happening, people were going in with a certain amount of money and coming out with a different amount of money. So these are banks. And courts are established. So lots of amount of social fairness, or a concept of fairness. This is one of the monsters which is studied a lot in biology. And we know basically everything about every action, about every interaction of these 500,000 players. So maybe it's the first time that it's complete information about the human society. Maybe Google has better data. Certainly it has better data. But 10 years ago when we started it, we thought that this was true. So we have information about the states of the players at any point in time. And we have the information about the interactions. Yeah. And since this is a self-contained game, there's nothing else. We have the whole context all together at the same time. So we don't have to cut out anything from this universe to study. We have everything always in the entire context, which you can never do in reality, if you're a sociologist or social scientist, you can never do. You have all the factors for some cause that's leading to some effect. You have all the possible reasons there, encoded in data. If you find it, if you can figure out how the effect came into being, given certain causes, it's a different story, but all the information is there. What do you do if you know everything? We can ask different sets of questions. So how do people interact? You have a question? No? No? Okay, looks like it. So how do people interact? As I showed you on Sunday, we have at every second, we have the state of the friendship network. That's the green network. It's links, directed links. Very often they are reciprocated links. Reciprocated means link points in both directions. Friendship, I like you, you like me. That's what the green lines say. The red lines are enemy arrows, enemy links. So many people hate this person did something wrong. So many people mark this person as an enemy. After a day or two, you remove that link, typically. Yeah, so this is not, the enemy ships you very often remove. Very often the friendship things you don't remove. They're much more stable. This is the communication network between the same set of people. So on one day, the weight of the link tells you how often they have communicated on that particular day. So here's this is time, and this is a couple of network measures. This is the number of nodes in three different types of networks. This is the number of nodes in the friendship network, that's the green one. the communication network, that's the black one, and the red one is the enemies. The number of nodes over time. So the game exists in 4 copies of each other. There's 4 universes, and doesn't matter. This is the number of links, how they increase over time. This is the degree, the average degree over time. This is the clustering coefficient. This is the clustering coefficient in relation to the clustering coefficient of the random graph. Maybe you have heard that you should always compare network measures to something, to a reference thing, and that is very often the Erdős-Rényi graph. So it's the clustering coefficient with respect to the Erdős-Rényi graph. What we see here is that enemies have very, very little clustering. Friendships, the green, and communication have huge clustering, meaning many triangles. So I don't go through the other ones. This is reciprocity. No, this is reciprocity. No, this is reciprocity. This is undirected reciprocity. So we can now use these networks to test certain social science hypotheses. There's 2 extremely famous ones. Both are from the same guy, from Mark Granovetter. One is the so-called weak ties hypothesis. I will say in a second what it is. Weak ties hypothesis state something about links that link communities. We'll see the statement, what it means, and triadic closure. Triadic closure is another mechanism that says that if you find yourself in a situation that if this is you have 2 friends, you will make sure that sooner or later your friends also become friends. You're closing open triangles. So, what is the weak ties hypothesis? It says that the degree of overlap of 2 individual friendship networks varies directly with the strength of the tie to one another. Clear? So the degree of overlap of 2 friendship networks. What is the overlap? The overlap is a measure, a network. Have you learned it? Maybe the overlap, maybe you don't learn. The overlap is a number between 0 and 1. It's 0 if I and J only are linked directly to each other and their friends are not linked. The overlap is the percentage of your friends that are also friends. The overlap is 1 if I and J is linked to each other, and their friends are all of their friends, all of friends of I and J are also friends of each other. Okay? What is the strength in a friendship network? There's many ways of measuring strength. One is we can count, for example, how often are we communicating. Yeah? So that's the strength. So the overlap is this. The strength is, let's say, the number of exchanged messages between people. Let's discuss betweenness, link betweenness. So statement is no strong tie is a bridge. So a bridge is a node. That's an old word for link betweenness. Link betweenness is how often do I have to go through that link if I want to connect any 2 nodes in that network compared to all possible paths there are. It's all the pathways to go from I to J that go through link IJ compared to all the possible paths from N to M. Okay, so this is betweenness that you have learned. And that's the formula. Now we can take the friendship network, for example. We can compute the betweenness, we can compute the overlap, and we find this power law. Of course, it's a power law, complex system. The slope is negative 0.5, it's 1/2. We can measure the strength between two nodes, how often do they communicate, and the overlap. We find another power law with 1/3 of a slope. And if we have betweenness is this, and if we have strength is this, that's what we see in this plot, we can compute a Kepler law. So the physicists will understand, because Kepler law has an exponent of 2 on one side and a 3 on the other side. This is a remarkable finding. Why is it remarkable? Because the link strength is something very local, and betweenness is something very global. For computing betweenness, you need to have the complete information about the whole network, and the information that's captured in it tells you something about the strength. So it's kind of amazing.
It is weak, then it's strong, it's 1.
It's so hard to understand.
So if there is a weak ties between that I and J, it's
Yes.
0, and if it is strong, then it's 1. So can we connect with time?
Connect with time?
Yeah. Just imagine we are in the space, we are in the program, okay?
Okay.
So at the beginning, we are no friends with each other.
Yeah.
But day by day, we
Yes.
are now growing and
Yes.
we are now friends to each other, and at the end, we will become one. So is it possible to connect?
It would be possible. This is just from a snapshot. This is not there's no time component in it. But so yeah, it's a snapshot from a time where the networks reached a more or less stationary state. Of course, one could look in the transient what is happening with this in the beginning of the game. Okay, so we don't know what's the use of this. No idea. Maybe some marketing people will find an idea. But if we have something like Kepler's law, is there Newton's law? So, what is a force? In physics, a force is the exchange of something. It's typically, electromagnetic force is the exchange of virtual photons. So if you have two charged particles, an electron and a proton, for example, there's virtual photons that are exchanged, and through that exchange, the attractive force is created, is coming into being. So we need a space, we need an exchange, we need time. In the Partha's game, we have space. We know where people are, and we know the relative distance. This is the space in the Partha's. This is the different cities we have there. We have space, we have people, and we have exchange. So people exchange messages, for example, or they exchange gifts, and we can ask, conditioned on how much they exchange, will they change their relative distance? So people that talk to each other a lot, will they get closer in time? Now we have time. Or will they get further away? So now we can look at Newton's law. Force is the derivative of a potential, and we can measure this potential. This is kind of interesting. So we can measure the potential for the different interactions, for exchanging messages, for attacks, for being friends, and they all follow more or less a quadratic form, as we have in the harmonic oscillator. Very strange, except for attacks. If you zoom into here, attacks has a minimum in the potential, which is about 3 to 4 lattice distances away. This tells you what This tells that people that attack other people never get really close. They always keep a safe distance. And the average safe distance is where this minimum is. So you hit someone and go away, or you do something bad to someone. For this, you have to get close, and then you immediately separate again. So I also don't know why one could use this, but you can measure forces of people depending on what they are exchanging. So we thought that was a kind of a nice analogy to physics. Next thing is, how do people organize? So we talked about this on Sunday. If you have directed links, these are the 6 open possibilities that you have, and this is the 7 open possibilities, 7 closed possibilities that you have. And we can measure the rates at which open triangles of a specific kind form closed triangles of a specific kind. These are the transition rates as measured. If you want to build an agent-based model where you have rearranging social links, you can use these transition rates to model a realistic rewiring. And what you clearly, what you don't see clearly here, you see more clearly here. On the x-axis, we show the open triangles here and the closed triangles here. And on the y-axis, we show the z-score. So how many of these triangles do I observe in the game? Now, if I count 700 of these open triangles, what is this? I should compare it to what? To a random graph with the same number of links and the same number of nodes. If I do that and compare it, if I take it into relation, the counted number divided by the number I expect from the random graph, I get the z-score. Yeah? If the z-score is negative, the observed triangles are underrepresented with respect to a random model, random graph. And if it's above 0, it's overrepresented. So the open triangles for friendship, that's green, or communication, that's black, are underrepresented. The closed ones are overrepresented. If you look at if a negative interaction, meaning being enemies, negative interaction, it's not a nice interaction. So for bad interactions, the open triangles are overrepresented and the closed ones are underrepresented. I showed you this. If you take it seriously, that the component of closing triangles is really important, is really a driving force in how the Homo sapiens is building social networks. If we only take this component into consideration, how much of the observed networks characteristics can we understand? And for this, we came up with this extremely simple model that at time step t, we have this kind of network with probability r. We close a triangle, we close this link here, 1 time step in the future, and with probability 1 negative r, we're not closing it, we're just establishing a new link to someone else. And if we're doing this, we can look at three different network measures or network functions, all a function of the degree. It's the attachment kernel. Have you heard of this? Attachment kernel is the probability that a new node is linking to an existing node, given you know what the existing node has, what degree that the existing node has. So this is the degree of the existing node, and the y-axis is the probability that the new node links to it. If that is a straight line, that is called, it's a test for your first, it's called preferential attachment. Yeah. And the slope of that line is the alpha in the preferential attachment, if you have an alpha. Okay, this is the friendship network, the communication network, the trading network, and the model is the data is the red dots, and the model is the blue dots. You can read off everything in the game. So this is a parameter-free model. You cannot fit anything. It comes out right or it comes out wrong. It comes out very, very close to the observed data. This is just a degree distribution for friendship, messages, and trade. Perfect agreement. So we can understand the degree distributions of social networks as a triadic closure phenomenon. And if you plot the clustering coefficient as a function of the degree, in the data you get this red curve, and in the model you get this blue curve. So it's a little bit different, but if you're very tolerant, you would say the red thing is more or less a power law, if you're generous, as I told you before. And if you're equally generous than to the model, then you would also say it's a power law there. Here you are a factor of 2 off. So you make an error of a factor of 2, but the exponent is correct. So I'm not going to go into this. This is the next interesting thing. These are again degree distributions for friendship, communication, for trading. It's cumulative degree distributions is the degree. And this is the probability that you blindly grab into the network, pull out any node, that this node has exactly degree k. That's the degree distribution. You see, for the positive ties, friendship, communication, and trading is you need to have trust to have one of those. It's not Erdős-Rényi graphs, but it's something like Erdős-Rényi graphs. It's falling off quicker than a power law. It's not a power law. It's falling off. Whereas for the negative ties, being enemies, attacking others, and putting bounties on others, you find power laws. What does that mean? If you find power laws, that means you have hubs. You have a couple of individuals that attract lots of enmity. That's what we have seen in this one of the first plots. One guy was hated by almost everyone. That's why we get people that are hated is a power law. People that are hating, that are marking others, is not a power law. Yeah? People that are being attacked is a power law. People that attack others is not a power law. And people that put bounties on others also show a power law. So aggressive networks that come out of aggressive actions are scale-free, a power law. The other ones are more random. Sure. No. This is all from the computer game. From the friendship network of all of the players, who is friends with whom, we count what is the degree of everyone. In the friendship network, in the trading network, in the communication network, in the attack network. The attack network is if I attack you, I have one link towards you. If you attack me back, we have a reciprocated link. And then we take these matrices, sum over the rows, plot the histogram of that, sum over the lines, and plot the other histogram. And the different line sums is black, row sums is blue. Okay, I'll jump over this. Now we could look how the different types of interactions influence each other. What is the network interaction? It's a complicated thing. It's very tedious, but if you want to understand how societies work, it's maybe a way of doing things. Yeah, no, I'm not gonna talk about this. We've seen this before. If we are looking at friendships and if we are looking at enmity at the same time, we can look at signed graphs, where links have a sign, or have two states, plus and minus. Here, everyone is a friend. Here, two friendships, one enemy, two enemies, one friend, all enemies. There's a big social science literature for 100 years almost that calls these triangles, where you multiply all of these signs and you get a positive result, you call these balanced. And if you multiply these here, you get a negative sign, plus times minus is minus. This is unbalanced. Minus times minus is plus is balanced. And here this would be unbalanced, according to the theory. But there's another school of social scientists who still call this balanced, just to make things confusing. We can compute the number of these triangles again. The number of triangles we observe. This is the number of triangles we would expect in a random graph. And we can ask how many standard deviations are we away from the random graph result. And we find this is overrepresented by 71 standard deviations. Huge result, right? This is underrepresented by 100 standard deviations. This is overrepresented by 50 standard deviations. So this is really, really happening as these guys were feeling, or where they had good intuition. And in this case, it's underrepresented by 5 standard deviations. In physics, 5 standard deviations is enough. For the Higgs particle, 5 standard deviations, if you can show that this is with 5 standard deviations, it's an effect, it's there. This is another completely not understood thing, was observed before. It's the Dunbar numbers. It's the Dunbar number. Do you know the Dunbar number? The Dunbar number is 150. That's easy. But what is the Dunbar number? That's the number of people you can keep track of in your brain. This is maybe the size that the Homo sapiens grew up with in evolutionary times for hundreds of thousands of years. 150 is a typical Homo sapiens size, living in the savannah somewhere in Africa. And it seems to be that we can keep in mind with our mental capabilities the information that pretty good information about 100 other people, so that it is meaningful to. And that's the Dunbar number. You find this over and over again, this 150, not only in humans, but also in primates and in dolphins and intelligent social animals. And the Dunbar numbers is the observation that people seem to cluster in multiples of 3. So if you look at the group size distribution, if you look at all the sizes of all human groups, you find that 3 is overrepresented, 9 is overrepresented, 27 is overrepresented, and 27 multiplied by 3, I don't know what that is 81, thank you. Remember that. Is overrepresented. And in the game, if we look at the group size distribution, we find, well, that's just yourself, we find these spikes in a logarithmic scale, and you can argue if these are equidistributed or not. There's maybe something missing here, but we see that groups in the game are more or less organizing in multiples of 4, not 3, but 4. Maybe because it's easier to keep information about others in the game than in reality. Maybe this is 4 and not 3. That's pure speculation, no one understands. But it's super interesting that it's also there in the game. We have talked about the behavioral code, that I, as a human being, am just a sequence of actions. In the game, here's an alphabet of actions: attacking, creating certain links, communicating, etc. And we can represent every life of every player as a sequence of links, a sequence of actions. And these actions are very often directed towards other players. So this we would indicate here. And then we have the same content, information content, as we have in the multi-layer networks. It's the same information here, just now focusing on the temporal aspect more than on the network aspect. And then we get these transition probabilities, for example. So this is saying at time t, if I communicate at time t, here, what is the most likely thing that I do in the next time step, t plus 1? Look at this. The most likely thing is that I receive a communication event. If I talk now, most likely thing is someone else talks to me in the next time step. Or the next likely thing is that I communicate again. I talk to you, and then I talk to you. Now I'm in the talking mode, and then, okay? So you can use this transition probabilities to come up with a Markov model. If you want to model social behavior, you could make a Markov model out of this.
What are the signs here?
Huh?
What are the signs
The sign?
Yeah,
the symbols? The symbols are the different actions. B means putting a bounty on someone's head. C means communicating. T means trading. X means getting rid of a friendship link. And the little r means received. I got it. I did not act it. Communication, CR means I received a communication from you.
So friendship is something
Friendship is here. I can receive it. You mark me. I mark you. Now it's inherent in the game. So I can mark you as a friend, but only use, not like Facebook. It's like Facebook, but only you see it, and only I know it. No one else sees it. You cannot brag that you have 2,000 friends. And if we are friends, I can dock my ship easier to yours. And we say we have a little bit of trust that when I'm sleeping, you can trade with my ship.
So all
okay, so this
have this behavior, right? All of the actions have this reciprocal behavior.
All of them. Everyone can do every action, so you can reciprocate everything, but you don't have to. So if you just look at the statistics that you can derive from these probabilities, is that the number of positive actions that you're doing is overwhelming. People are not aggressive. 97% of all actions are good, only 3% are bad. Why is this? Because if you are doing bad things to others, they will just reduce their links to you. And it's no more fun. Then you're alone, and what are you doing in this stupid world if no one does anything with you? Then it's pointless. So you're behaving automatically. You don't have to impose rules. But if you are receiving a negative action, something bad is happening to you, then you're becoming extremely aggressive. Then 25 actions out of 100 of yours will be aggressive. So you become an order of magnitude more aggressive if something happens to you. That's also an interesting thing, how you can boost, how the Homo sapiens boosts its aggressivity once it's attacked. We can, if we do a positive action, we can go up. And if we do a negative action, we go down. So we can make a world line for every player. This is if we look at many players. Most people are just doing positive things. They're always, those are going up. those who are doing many negative things, these people live very short. So you see the lifetime correlates with your...
But the originality of these actions, I think they're different, right?
Sorry? Unfriending someone is not the same as unfriending, no.
It's not the same, but you add them up.
Yes, so we want to, something that's unfriendly, we go down. Unfriending someone would be more unfriendly than friendly.
So they have weights? Do they have weights? How much better an action is?
No. It's just one down or one up. And this is not very, it's just to show that if you're an average, a mean guy, you're not enjoying the game. And the vast majority is positive. And we did this to see if war periods, if people become more aggressive but didn't show up. So if we have this behavioral code, it looks as if it was a DNA sequence. DNA sequence just has 4 letters. We have more letters. In this analysis, we just used 8 different actions. So we have an 8-letter alphabet. We could also have a 20-letter alphabet. Then we can look at different words in this alphabet. So what is a word? It's just a chunk. So we have our action stream, and we are cutting out segments of length n, and then we call these words. And we ask how often do these words appear? And then we have the probability of these words to occur. And this is this piece here. Probability for word I to occur, given that the word length is n, times log is the entropy for words of length n. Entropy should scale linearly with the size of the words. So if we're dividing out the length of the words here, this thing should be a constant if words were not correlated. Yeah? If we plot this as a function of word size, we see that this is, of course, not at all a constant, and there is really meaning and information, structured information in these word sequences. Here is, if we take these sequences, we can also ask what's the most frequent word? We plot it here. The second most frequent word occurs how often? Half of the times of the most frequent one. The third most frequent occurs x divided by 3 times. This is Zipf's law. It's not true for the short words, but for the longer words from length 6 on show Zipf's law. So again, this is we went through this. We can look at how do males and females locally network or build their networks. In the network, in the game, at the beginning you have to decide a character. You can combine and design your own character, but it must be either female or male. You can be human type or this type or this type or this type, but there's always a male and a female version of it. You cannot change afterwards. It's not like real life. So there's only 2 genders. Yeah, there's not a spectrum, and it's very old-fashioned. So now we can look at the different interaction types, and we can look at the degrees of males for friendship, for communication, for trade, and subtract the degree of females. And what do we see? It's around 0, meaning males and females have more or less the same number of friends. Here, degree of males negative the degree of females for communication is -4. Means what? Females have four communication partners more on average than males. Females have 2 communication trading partners more than males, and for the negative things, it's more or less within the error bars. So let's do it with the clustering coefficient. Females pick friends. Now, females have higher clustering coefficients for friendship, communication, and trade. Again, for the negative things, it's more or less the same. What does it mean? Females having a higher clustering coefficient with friends, they are building more triangles. They're embedded in more local triangles than males. So this is the nearest neighbor degree. You all have heard what the nearest neighbor degree is? You look at your neighbors, see what their degree is, you average over that degree, and that's the nearest neighbor degree. Males and females are the same everywhere, but for communication, males are picking communication partners that have a high nearest neighbor degree. Huge difference. So males try to communicate with people who get lots of information. They want to be informed. If you think of how these networks look like, they are trees. It's fuzzy. Yeah, it's not focusing on closing triangles. It's trying to get high speed information pathways in your network. So males are optimizing information speed. Females are optimizing stability. This is reciprocation. Females are reciprocating, meaning answering positive events more than males. They're nicer, and not so much. And for the negative interactions, it's more or less the same. This is again the degree distributions that we have looked at before. Males are blue, females are red. So you don't see much because it's logarithmic scale. But if we subtract males from females from this degree distribution, here's the difference on this side. So here we see, as a function of the degree, we see if females or males are overrepresented in communication trading networks. So what do we see here? We see that in friendship, males and females have more or less the same degree, except for very high degree, females are overrepresented. If you look at enemies, males are overrepresented for almost all degrees, except for extremely high degrees, women are overrepresented. So this means women are super lovers and super haters. In communication, the degree of females is overrepresented everywhere, except for those who communicate with extremely many people, and the males dominate. For attacks, this is only males. And look at bounties. A bounty is if I put a bounty on your head, if someone else does something bad to you, I pay him. This is what females are doing. So aggression is handled in very, very different ways, and you can just read it from the networks, from the degree distribution of these stupid networks. So we are seeing biology in the difference of the networks. We can ask about response times.
So I mean, this male and female, this is only in the video game, right? Because the person who is playing could be male, they could have chosen a female character.
Yes.
So, is there something in the game that gives the female character some rules that don't apply to males?
Nothing. We know from an experiment that we did that we have about 30% of the people are switching their gender. Females playing males and males playing females. But when they choose to play, when a biological male plays a female, he acts as if he was a female very often, in many different ways. If I mark you as a friend, I start the clock and count how many seconds does it take until you respond by saying, I'm your friend too. So we're measuring response times. Here's the time, and here's how long does it take to respond, time to respond. And we get these characteristic curves, and I interpret them now for you. If a male marks another male as a friend, it takes quite a while before the response comes, a couple of days on average. If a male marks a female as a friend, it takes forever to get a response. But if a female marks a male as a friend, the response is almost immediate, within seconds and minutes. So again, completely different biology. And for the negative action, if I mark you as an enemy, as a male, another male, the response is immediate. Let's fight, enemy. And if a female marks another female as an enemy, no response. It's very often no response or a very delayed response. The conflict is ignored. So again, different handling of conflict. So here you have these funny looking curves. This is not a power law. This is a semi-log plot here. If you plot semi-log in a semi-log fashion, the decay rates of atomic substances, metals, you get straight lines. This is the decay law. But if you're making an alloy out of it, you're getting these funny curves. Look at this, not the red curve, but this one. These are very similar to these ones. So it's maybe that that the shape of these curves are showing that we have a mix, a heterogeneity in the population. So different response times, characteristic response times in the population. I don't know if this is true or not, but it's funny. And the last thing is, what is the clock saying? Oh, I'm out. For how much time have I overspent already?
4 o'clock is another clock.
But I'm eating your tea time. Very quickly. So the only thing we could do is to measure with a price. So we said if you play this quiz, if you answer this question, you can win a weekend on this island. For this, you have to send us, of course, your real name for the ticket and the avatar name. So 10,000 people responded, and from this we read off how many are gender swapping. This we can do, but we did not try to measure real wealth or things like that.
What percentage of actual players were playing those? Like actual players, I think they're predominantly male, right?
Most of them are male. So more than 60% are male. But it's not as bad as in other games where you have 95% male. So yeah, it's not a fighting game. So it's more females than. So in the game we have a wealth distribution. That's the blue line, which is if you take the conversion rate. If you fix the conversion rate between the English pound and the Partha's currency, if you shift that, then you can put the English wealth distribution right on top of the Partha's curve. You can put the Swedish curve, wealth distribution right on top of this Partha's curve. And from this you can compute the Gini coefficient. The Gini coefficient is a number between 0 and 1. It's 0 if everyone has the same share of the wealth in the system, and it's 1. No, The actual world is the triangles, that's Sweden, and the circles are UK, and the blue line is the game. So it's almost the same for 1, 2, 3, 4 orders of magnitude. So this is really surprising. So this is the Gini coefficient, how it varies over time. And here is an event that we triggered artificially. At this point in time, we made a charity where rich people could pay into a big fund. And on Christmas Day 2009, this fund was distributed to the most poor in the game. So they all got richer. And that showed up in a change of the Gini coefficient jump on one day. And we were expecting that the redistribution of wealth would now fluctuate down here. But within a couple of days, we were back up to the previous levels. So it's a sign that it's extremely hard to redistribute wealth in a naive way. If you just give money to poor, they will buy status symbols and the money is gone and nothing changed. They're back to where they were, but they have a nice car. And in a year, then it's all lost. If they're not investing in changing their behavior by education or something, then it's lost. We are very proud of this because it was used on the homepage and in lectures of a finance minister of Greece, a very rebellious finance minister that was steering Greece through its financial crisis. And he was using our plot in his talks to show how complicated this is. This is the finance minister. This is not really the case. He was, in Europe, this is funny because he was showing this finger to the German chancellor, which he should not have done. So what determines...
So this, you said naively give money, it won't go down. So, but this was just at one point. Like, what if we sustain it? Every month you give?
Yes. We don't know. So what determines why are some people rich, why are some people poor? So we thought what should determine it is your position in the social multi-layer network. What is your position in the social multi-layer network? The social multi-layer network is a very high-dimensional object. It's not the position of the social multi-layer network has many dimensions. One dimension being, for example, the degree of the friendship network. Another dimension is the degree of the trading network. Another dimension is the clustering coefficient of the bounty network. Another is the nearest neighbor degree of the, of any of those. So it's, 100-dimensional space. And you can not visualize it, but you can make cuts, 2-dimensional cuts through that space. And here's some cuts through that space. So here's the degree of, we don't look at this. We look at these two. This is the in degree of trading. This is people that trade with me. This is the out degree of trading. So what do we see here? If I have a large in degree, if many people trade with me, I'm getting rich. Rich is this red. Red is rich, blue is poor. If I have large out degree, I'm not so rich as if I have a large in degree. Why is that? If others want something from me, I can set the price better. Okay, that's what you see there. Here's another interesting thing. This is the undirected degree in the trading network, and this is the nearest neighbor degree in the trading network. The more I trade, the richer I am. Okay, that's trivial. But what does it have to do with the nearest neighbor degree what does it have to do with the degree of my neighbors? If my neighbors have very low degree, I can sell them stuff, but they cannot sell it. Right? So that we're not in a supply chain. It's not a thing that is scaling. If my neighbors are super connected, they're usually very, very good. Maybe better traders than I am, and they will dictate the price. Or they are smarter than me, or are better positioned, so they dictate the price. And I'm also not rich here. But there's a sweet spot where you can do well. Okay, and there's hundreds of other cuts that you can make. Many of them are more or less reasonable. And the conclusion of it is, if you want to understand where wealth comes from, you have to give a lot of answers. Maybe a dozen of answers. Some of them, or most of them, are here. You can find regions in your social multi-layer network space where that determine if you are there, you are rich. Okay. Is that the last slide? Looks like it. Yeah, yeah. So this is not the conditions why you're rich. This is the last slide. This is the conclusions, what I've told you. We can measure the strength of human interactions. If it is really a Kepler's law or not, we can argue if this relation holds or not, but there is a relation, a very strong relation. We cannot argue if we can measure the potential between people, given a different interaction type. This is there. Humans organize in triangles. Humans organize in groups of roughly 4, and multiples of 4, 16, and then I cannot do it, 36. Males and females organize in, localize the local neighborhood in very different ways. Females try to optimize stable networks, and males optimize information flow on networks, or their position in information flows. Females and males handle aggression very differently. Humans boost their aggression levels if they are treated badly. And wealth is a function of your position in a social multi-layer network, and that function is complicated. Thanks. More questions?
This is last